14 one-time pad. In order to communicate securely with Santa while you're on this mission, you've been using a one-time pad that you generate using a pre-agreed algorithm. Unfortunately, you've run out of keys in your one-time pad, so you need to generate some more. To generate keys, you first get a stream of random data by taking the MD5 of a prearranged salt, your puzzle input, and an increasing integer index starting with 0 and represented in decimal. The resulting MD5 hash should be represented as a string of lowercase hexadecimal digits. However, not all of these MD5 hashes are keys. You need 64 new keys for your one-time pad. A hash is a key only if it contains 3 of the same character in a row, like 777. Only consider the first such triplet in a hash. One of the next 1000 hashes in the stream contains the same character 5 times in a row, like 77777. So it has to contain 3 of the same character in a row. The first the triplet, and then one of the next 1000 hashes contains that same character 5 times. Considering future hashes for 5-of-a-kind sequences does not cause those hashes to be skipped. Instead, regardless of whether the current hash is a key, always resume testing for keys, starting with the very next hash. Okay, if the prearranged salt is ABC, the first index which produces a triple is 18 because the MD5 hash ABC18 contains 8888. However, index 18 does not count as a key for your one-time pad because none of the next 1000 hashes contain 888. The next 1000 are 19 through 1018. And then we have 39 that contains the next. And then you find some more blah blah. And then you have the 64th key. So index this one produces the 64th key. Given the actual salt in your puzzle input, what index produces your 64th one-time pad key? Puzzle input is this. Okay, let's just try with ABC. We have none of this anymore. Salt, it's ABC. How does it work with the hash? Message digest dot get instance MD5. Then we digest and zero, I guess. Start at 0. Input. Count a string. Then we digest the input dot byte array. Then we have a byte array. Yeah, I wonder if that's the way it worked. Let's check it. So we have ABC18 produces this. Okay, we can't really do toString. Mm, how do I get it to string again? Something with this presentation, like this. Mm, yeah, okay, 888. Cool, we have this 888. So now we need, well, we need to check if this one has three consecutive the same. Mm, 0, string dot has three. Okay, so so I if the child index I is the same as I plus 1 and I plus 2, then I have 3. I just loop through. Let's do simple for loop. So if I have 3, I need to check the next 1,000 if they have 5. So I need kind of the same thing. Or even I can go count to count plus 1000. Each of those I go the same. Hmm. Oh, so if this one has 5, I can add to my result set. Add C. And then I need to break. Okay. And then I can do okay, so then we just loop that. So the plan is y result size is smaller than 64. Get an input out of sort and count. Get a message. From the input. Hmm. We can just call this here check. It could do everything. And then we say, does this as well. Okay. Okay, so when we have now we're looking for filling a results list. We get based on the salt, ABC and account, some input if it has three, I think, after each other, then we check for five. Similarly, here I can also use check. Check basically gets salt plus count to string and makes the MD5 hash of it, turns into a string. And I can check five consecutive. If I do it on an auto list, then I stop looking in this part. I don't know if I need to skip 1,000. Let's see if it works. Okay. Adding 200 here constantly. Why? 1836. 720 is the last one. But here it's 200, 222,000. Did see that thing with the 200. Oh, wait. I just checked for fast five, but I need to check the same letter. Nice. So we need to add, oh, we need to add the condition that it checks the same. So if there's 888 here, then the other one has to see 88888. So that's the char here. We get from the 3. Hmm. Now I'm somehow losing the 18. I don't know why. I get this 8. Ah, no, I want to lose the 18 because the 8, none of the next 1,000. And then the first one is 39. Okay, that's cool. And then it has EE, none of the 6 triplets are keys. One after that. And then we have, no. Yeah, do we have that as well? 92. And 2 is the last one, but we have 23, so maybe we need one more entry, or no, doesn't make sense. And maybe we need to continue after count plus 1,000. No, now we're skipping 92. Mm, that can't be. 64. Maybe I'm checking one too many. I am checking one too many. Still. Oh, I'm checking count as well. You check the next one. Yeah, okay, now I have the right number. So let's try the puzzle thing. What was changed was I have to start one further than count. And then go to count plus 1,000 to do the exactly 1,000 more. What's the question actually? What index? So the last one here reduces the 64. Okay, that's the correct answer. Of course, in order to make this process even more secure, we've also implemented key stretching. Key stretching forces attackers to spend more time generating hashes Unfortunately, it forces everyone else to spend more time too. To implement key stretching, whenever you generate a hash before you use it, you first find the MD5 hash of that hash, then MD5 hash of that hash, and so on. 2016 additional hashings. Always use lowercase hexadecimal representations. I wonder if that's the one. Step. Only hexadecimal uppercase and bytes properties affect the formatting result. Lowercase. Uppercase is set to false. If you use uppercase property, it goes uppercase. Coolio. Then 126 additional hashings. Mm, okay, so let's use it this right amount of times. ABC0 should turn into this. Check. Mm, okay. Check. ABC0. Okay, we have the A10, blah, blah, blah. Okay, and then what index produces 64th hash? You just have to let it run. We just changed the check method. Hash is way more now. Takes pretty long. Yeah, even just testing takes super long because of all the rehashing. Hmm. Maybe we can save some time with hashing because you're checking here twice. So if I do um, string, oh yeah, you can save a lot of time because every time you start a count, then you check 1,000 times more, and then you start at the next count, but here, but could be that you already checked it, so you don't need to recheck it again. So with a small hash map optimization, you can really speed it up. Let's see. This is right. Oh, am I still ABC? No. Yep, that's right. Okay. So yeah, we just hash 2017 times. And the trick is to use a map to not recompute the same check evaluation if you already passed it, because you do pass it more often because you go to check for the input and then you check again if in the next 1,000 steps there's another hash that has 5. So just saving this method, improving this, makes the algorithm fast enough. And that's it.